Hello everyone, welcome to my channel. So today we are going to do Leetcode weekly challenge. Fourth question, count the number of good partitions. So here let us first read this question, then about the constraint. Then on the example we'll test it how we are required to code for the same. Because after getting into these examples, then only we will be able to understand that how exactly we are required to code this question. So here let us first read this question. You are given a zero index array num consisting of positive integers. A partition of an array into one or more contiguous subarray is called good if no two subarray contain the same number. So basically, here we are required to do the partition, and that partitions in those partitions the thing would be that whatever number is there, if duplicate are also present for that number, so that should be present only in a single partition, not in that other partition. So that's why then only that would be known as the good partition. And we are required to return total number of good partitions of the nums. So since the answer may be large, we are required to return modulo of our answer. So now here we can see as per the constraint, it is 10 raised to power 5, means n square solution won't work. Only n or n log n solution would work. And as e digit 10 raised to power 9, so that's why they are saying that we need to do the modulo. So now, if we check this first example which is given to us, now the thing is that we are required to return the possible good partitions, right? So if we check here, if we do partition at this particular point, minute, if we do partition at this point 1, right? So other would be 2 3 4. So now we are able to get two subarrays if we do partition at 1, because each partition will give us two subarrays. That would be the thing. And here now if we do partition at 2, so again it will give two more subarray. If we do partition at 3, then it will give more two subarray. If we do partition at 2 or at 4, it will give another two subarrays. So basically if we do partition at 1, then it will be 2 3 4. If we do partition at this 2, so it will be 1 2 3 4. If we do partition at 3, so it will be 1 2 3 and 4. And if we do partition at this 4, so 3 4, then it will be uh 4 1 2, it is this. And if we do at 3, then it is 3 4. Mhm. 1 minute. Yep. So 1 2 3, and it will be 4. And if we are doing partition at 4, so then if we see that that was already included here, but the thing was that the whole subarray itself is one partition, and as all are unique, right? So in that context, individuals which are there, that also become in itself a partition, means basically these. So to in total, for each unique number which is here, for the fact that they don't come in two partitions at a particular time, means basically if we do a particular partition here, then it shouldn't come here also and here also. Then only if they come at this particular point of a partition, only both of those, then only it would be a good partition, else it won't be. So this is which they want to convey here. So this is from the first example. And now in this, we can see all are duplicates, so no good partition is possible. So in that context, the array itself is one single partition. Now we take example of this. So here one, if we do partition from this side, minute. If we do partition at this one, so we can clearly see that it will become 1 and 2, 1 and 3. But here one is here also and here also, right? So that's why it is not a good partition. So if we do partition at 2, so it will become 1, 2 and 1, 3. So again one is here also and here also. So again it is not a good partition. So if we do partition at this one, so it becomes 1, 2, 1 and 3, right? So it gives us two sub arrays and the whole array itself is a good partition. So in that context, now our answer would be two possible good partitions. Basically, each partition will give us two subarrays. So that's why whenever we are doing a partition, it will in return give us separate two subarrays. So basically, whatever partition we are doing at that moment, we are basically having two options. Either we can continue with whatever subarray we are continuing, or we can start a new subarray. So that's why whatever partition we are making, we can get possibly two results at that particular point. So in that context, at a single point of time, we can easily return two results. Means basically two possible partitions which could be there. So here if we see in this example itself, here if we stopped here, as no good partition was there, here also no good partition, we are continuing here also no here, but we got a good partition. So one possibility was there that either we can continue with this whole, so it will give us the whole array, right? Or the thing was we can directly split it into two. So that's why at a single point of time we can get two answers. So that's why there were two possible good partitions at that moment of time. Here if we see, because we can't make any good partition at a particular time as all of them are equal, so that's why the original array itself was the answer. Now here 1, 2, 3, 4. Here we can clearly see that the number of unique elements and the way they are arranged, that all are unique one after other. Here you can see that there are three unique elements, but still the way they are arranged, so we can only make partition at the latest occurrence of that one, means a latest occurrence of that duplicate element. So that's why in that context the partition was reflected. So that's why here we are making partition at this particular point of time. So in that context only we are required to code our solution. So now let us go ahead with the coding part for the same. So here, as per the third example which was given, because here and even the second example where duplicates are there, and the question itself it is mentioned that there are duplicates. So that's why in that context, what I'm doing is I'm just taking an unordered map which will store the latest occurrence of that particular element, and here it will store the latest occurrence of all the elements. And now the thing is that I will be doubling the result at that moment only when I is basically greater than j. That simply means is here I is starting from the starting point only and j is also starting from the starting point. But j has stored all the but j has basically stored the last occurrence of the present element which is there. So at this point, if I is greater than j, then surely we can make a good partition at this particular point, and that will give us two subarrays at that moment of time. So that's why we are doubling the results and doing the modulo with the same. Else we are directly returning the result. That is, we are continuing with the subarray because here there is no good partition. And here we are just checking that what is the latest occurrence of the j. So the thing is that if I is less than or equals to j, if I is less than or equals to j, that simply means that we are required to go ahead with whatever subarray we are continuing with, because we hadn't encountered the latest occurrence of that particular element. But when it becomes greater than j, means I simply becomes greater than j, then at that moment we can directly go ahead and make our good partition. And as there is possibility that when we make the good partition, we have again the chances that we can continue with the complete that particular subarray, or again we can split it into two and make the partition. So that's why here it is multiply by 2, and we have taken modulo side by side as it was mentioned in the question, and then at the end we are returning the result which is required. So the time complexity for this particular question is order of n, and the space complexity is again order of n because we are taking this unordered map. So this was all for this particular question. If you have any doubt, you could comment that down. And if you like the explanation, you can like the video, subscribe to my channel, and do share among your friends. So this was all. Thank you.